Welcome to the deep dive. Today we're looking at something really fundamental, how AI goes beyond just seeing the world to actually, well, understanding it. How things work, what causes what might happen next.
Yeah, it's that core intelligence piece, isn't it? Easy for us, but incredibly tough for AI, especially when you move past language into, like, images and video.
Exactly. And that's why we're diving into this system from the Stanford Neuro AI Lab, Probabilistic Structure Integration, or PSI.
Yeah.
It's not just about slightly better predictions.
No, not at all. It's really about building these self-improving world models. Models that learn, adapt, and critically discover new ways to grasp visual stuff on their own.
And what really grabbed me is this idea of giving AI the kind of flexible control over visual data that we get with language models now.
Right, like prompting an LLM but for pixels, asking what if visually without leading text. It's about teaching AI the language of the physical world, motion, depth, objects.
So our mission today is to unpack PSI's three-step cycle, how it builds these models, how it kind of discovers the physics of a scene without explicit rules, and then uses that to get smarter.
Yeah, you should walk away understanding how these models see, how they interpret motion and depth, and why this self-improvement loop is so powerful for AI interacting with, the real world.
Okay, let's get into it. The foundation is this model they call psi. It's a probabilistic predictor.
That's the starting point. Think of learning a complete set of possibilities from raw video data, like tons of internet clips. It's not just making one guess about what happens next.
It's learning the whole probability distribution.
Precisely. Imagine a video frame as this huge web of tiny patches. He figures out all the rules, the probabilistic rules of how these patches connect and influence each other over time.
Not just one outcome, but the whole range.
Exactly, because the future isn't fixed, right? There are multiple ways things could unfold. So it gets that uncertainty. It knows an object might move this way or maybe that way and assigns likelihoods. That's absolutely key.
But video is so complex, high-dimensional, it doesn't have that neat left-to-right structure like text. How does A handle that?
That's where the local random access sequence modeling, or LRAS, comes in. It's a really neat innovation.
LRAS.
Yeah. So traditional AI struggles with video's lack of order.
Yeah.
LRAS treats it like language. It breaks the video into patches. Think of them as visual words. Then it mixes in two kinds of tokens. Pointer tokens say where a patch is, like coordinates, and content tokens hold the actual visual data, like the RGB color values.
So location and appearance.
Basically, yeah. And this structure lets them use the same kind of powerful training methods developed for large language models, which is a huge advantage for scaling up.
And those pointer tokens, they let it jump around, not just process pixel by pixel.
Exactly. It's not stuck in a rigid scanline order. It can access any patch anytime. That's the random access part. And it unlocks incredibly flexible ways to query the model.
Makes sense.
And there's another bit, the hierarchical local quantizer, HLQ. It encodes each patch locally.
Why is that important?
Well, it means if you change one small part of the image, it doesn't unpredictably scramble things far away. It keeps changes contained, which you absolutely need if you want predictable control over a scene. Makes the whole thing more stable.
Right. Localized cause and effect.
Got it. And all this, the probabilistic nature, the random access, the local encoding, leads directly to what they call rich controllability.
Meaning you can interact with it in lots of ways.
Yep, without any extra training for specific tasks. For example, unconditional prediction. Give A frame 0, and it just generates plausible next frames, exploring different ways motion could happen.
Okay, predicting the future.
But you can get way more specific. Patch conditional prediction. Give it frame 0, and maybe just a few key pixels from frame 1, like hint where something moved. And A will fill in the rest of frame 1 consistently, collapsing the uncertainty around your hints.
That's cool.
And here's the kicker. You can feed it synthetic patches. You can basically draw a little arrow and say, what if this bit moved over here?
Like directing the scene.
Exactly. You're performing a counterfactual query, and the model synthesizes a physically plausible outcome based on your intervention. That's incredibly precise control.
Wow.
And it works for the camera, too. Camera conditional prediction. Tell Tay to imagine the camera moved left or right, and it generates the new viewpoint, even filling in stuff that was previously hidden.
It hallucinates the occluded part.
Yeah, in a geometrically consistent way. And because it's probabilistic, it can also show you where it's least sure these entropy maps.
So you can see the uncertainty.
Right, which is useful. You could tell it, focus your effort on generating these uncertain areas carefully, or just generate everything quickly in parallel if you don't need maximum fidelity everywhere.
Okay, so A is this amazing controllable predictor, but it's still working with pixels. The next step is actually understanding the structure, right?
Yeah.
Moving beyond just pixels.
Exactly. That's the structure extraction phase. The goal is to get at things like optical flow, how stuff is moving, or object segments, what pixels belong together, or depth. Stuff that usually needs supervised labels.
And PSI does this without supervision.
Yeah, in a zero-shot way, using causal inference. It's like the model asks itself, if I mentally nudge this part of the scene, what else moves or changes? It compares the normal prediction with these hypothetical, counterfactual ones.
Like poking the model's understanding of physics.
That's a great way to put it. It's prompting, but visually, with these structured what-if questions.
Okay, give me an example. Optical flow motion, how does that work?
So imagine placing a tiny hypothetical tracer dot on an object in frame 0. Then you see where it predicts that dot will be in frame 1. It looks at the shift in the probability distribution for that dot's location. And that shift reveals the motion, the optical flow. What's cool is that because this sub is distributional, it gives really sharp, clear motion predictions, even if there are multiple ways something could move, unlike older methods that might just average things out into a blur.
Better motion tracking. Makes sense. What about objects? Figuring out what pixels make up one thing.
For object segments, it does something similar. It takes a patch from an object in frame 0 and then hypothetically moves it in frame 1.
Like the counterfactual thing again.
Exactly. So it knows objects tend to move as a whole unit. So if you hypothetically move one patch, it figures out all the other patches that belong to that object must also move to keep the scene physically plausible.
So the inferred motion defines the object's boundary.
You got it. By calculating the flow resulting from that hypothetical move, it highlights all the pixels moving together. That's your object segment. It's clever because it can even figure out the shape behind things that were occluded.
Very neat. Okay, last one, depth. How does it get 3D structure?
For depth, it uses the camera conditioning idea. It tells itself, okay, generate the next frame, but also imagine the camera shifted slightly sideways.
Creating a fake stereo pair.
Precisely. It generates this novel viewpoint, then it computes the optical flow between the original view and this new hypothetical view. The thing shifted. The parallax tells you how far away they are. That's depth.
And because A generates good novel views, the depth is accurate.
Yeah, it's geometrically consistent, especially around tricky object edges.
So flow, segments, depth. These aren't just outputs. They become new types of information the model understands.
Exactly. They become new token types. It's like adding motion words and geometry words to its visual vocabulary. It can now read and write these structures, not just raw appearance.
A richer understanding.
Definitely.
Okay, so we have predicting, and we have these extracted structures like flow and depth. But just having them isn't enough, right? You could end up with dozens of separate models.
Right, a whole zoo of specialized models, which is inefficient and they don't learn from each other. This brings us to the third, and maybe the most elegant step, integrating structure.
Unifying everything.
Yes. PSI provides a universal way to fold any extracted structure back into the same core M model. It's a cycle of self-improvement.
How does that integration work?
It's a neat three-step process. First, tokenize the new structures like flow vectors or depth values using the same local encoder, HLQ. Give them new pointer addresses, but crucially, use the same underlying vocabulary as the RGB tokens.
So no big architectural changes, the model stays the same size.
Exactly. Very efficient. Second, just mix in these new structure tokens into the training sequences. So instead of just frame 0, frame 1, a sequence might become frame 0, camera data, optical flow tokens, depth tokens, segment tokens, frame 1.
You're just rearranging the input sequence.
Yep. That simple change defines all the new tasks: predict flow from RGB, predict RGB from flow, predict depth, etc., all within one model.
Wow. And the third step?
Continue training. Use a careful learning schedule so the model learns these new mixed sequences without forgetting the old stuff, avoiding catastrophic forgetting. It just seamlessly integrates the new knowledge.
So it learns new tricks while keeping the old ones. The loop closes.
Precisely. Discovery leads to integration, which enhances the model, enabling further discovery.
Okay, what are the payoffs? What does integrating structure actually do for the model?
4 big things. First, richer control surfaces. Now, you're not just manipulating pixels, you can directly manipulate flow. Apply a few sparse motion vectors to an object, and A generates the resulting physically plausible movement of the entire object.
Like directly editing the physics.
Kind of, yeah. This gives state-of-the-art results on tough video editing tasks, like realistically moving objects around in a scene much better than, say, diffusion models can currently manage.
Okay, better control. What else?
Second, it improves the structure extractions themselves. Once the model understands flow internally, it gets better at segmenting objects, like separating a moving object from its static shadow, and its depth estimates become sharper.
So learning flow helps it see objects in depth better.
Exactly. The quantitative results show this clearly. Flow-based segmentation is way better than just using RGB, and the depth accuracy is top tier for self-supervised methods.
Makes sense. Third benefit.
Bootstrapping further new tokens. Because it now understands integrated structures like flow, it can start reasoning about higher order things. For instance, it can predict the probability that a patch will move even before it sees any motion.
P-motion. Probability of motion.
Yeah, imagine looking at a static picture of a room. This P-motion map can highlight which objects are likely manipulable before anything moves. That's huge for planning, like for a robot.
Identifying things you can interact with from a still image. Very cool. And the last benefit.
This one's maybe the most profound. It upgrades the underlying predictor. Integrating flow makes the model dramatically better at predicting future RGB frames.
How so?
Basic RGB prediction models often suffer from motion collapse. If they're uncertain, they just predict a static future because it's safer. But PSI, by first predicting the flow, the motion, and then predicting the RGB conditioned on that committed motion, forces itself to predict dynamic futures.
It avoids chickening out and predicting things won't move.
Yeah, basically. It commits to movement. And the result is significantly more realistic, dynamic video predictions compared to models that only look at RGB.
That's a really powerful feedback loop. Okay, let's make this concrete. Some practical applications. You mentioned video editing.
Right. Think physical video editing. PSI is like a physics engine you can edit. Take that bowling example. You edit the ball's path slightly in one frame. PSI doesn't just paste the ball somewhere else. It recomputes the whole future. The ball misses, the pins stay up. It respects the cause and effect.
A true do operation, changing one thing and seeing the consistent consequences.
Exactly. Or think visual Jenga. The AI can figure out which block to remove by hypothetically moving each one. But critically, it uses its flow understanding to imagine translating the block out entirely, including filling in the background realistically, what they call a modal completion. It's not just painting over the block.
It understands the block is gone and what should be behind it.
Yeah, much more physically grounded. And then there's the robotic motion map.
The P-motion thing again.
Right. A robot looks at a scene, maybe a table with tools and clutter. From just that single static image, PSI generates a map showing which things are likely movable.
So the robot knows what's graspable and what's fixed before it touches anything.
Exactly. It can plan its actions much more intelligently and safely, identify handles, levers, loose objects versus stable surfaces. It's anticipatory intelligence.
That really changes things for robotics. So, stepping back, PSI feels like a different way of thinking about AI learning.
It really is. It's a shift away from just training a big network and then trying to poke it afterwards to see what it learned. That's traditional representation learning.
Right.
PSI is more like the prompting paradigm we see in LLMs, but for vision. You query it, you interact with it causally, and crucially, it integrates what it discovers back into itself to get better. Probing becomes prompting, which becomes self-improving integration.
And it does this without relying on language labels for everything. It's learning directly from pixels and motion.
That's a key point. It forces the model to grapple with the actual structure of the visual world, the underlying physics, not just correlating words with images. It's learning a non-linguistic understanding.
Of course, it's not the final answer yet.
Yeah.
What are the limitations or next steps?
Well, currently, it mainly integrates local structures like flow. Integrating more global, object-centric representations is a big next step. Thinking about whole objects over time, not just patches. And then there are broader questions. Could this PSI framework apply to totally different kinds of complex data? Neuroscience signals, financial markets,
Interesting.
and maybe the Holy Grail. Can we get the AI to automatically discover which intermediate structures are most useful to extract and integrate instead of us having to figure out the right causal prompts for flow or depth?
Automating the discovery process itself, that would be something.
It really would.
So this deep dive really highlights AI moving from just recognizing patterns to, well, seemingly understanding cause and effect in the physical world, which leaves us with a thought to chew on.
Yeah.
If AI can genuinely learn the rules of physics interaction, just by watching and refining its own understanding, like PSI does? What completely unexpected things might it figure out? What kinds of interactions or physical principles might it discover that are maybe invisible to us, limited as we are by our own senses and ways of thinking?
That's a fascinating question. What could an AI, unburdened by human intuition, perceive about the fundamental workings of reality?
Yeah, exactly. Something to ponder. That's all for this deep dive. We hope this look at PSI gave you some new insights into where AI might be heading.